Hey, welcome back to Dr. Pat TV, looking at limits. So this is part two of our limit idea. Okay, so now in the previous video, we were looking at a couple of functions. The functions that we were looking at before had holes. So this is a second example, the second type of thing that can happen when we're dividing by zeros. We can create something we call vertical asymptotes. All right, so now with this particular function, when we plug in -3, we plug -3 in there. Of course, what's going to happen to us is we're going to have 0 in the denominator. Of course, that's a bad thing to happen. Things get kind of weird, get a little funky going on there. So let's kind of explore this one for us. Now, when we're doing limits, okay, again, recall that limits for us math people, they're really great. They're like our duct tape. They really help us work through some problems to see if the function's going okay. Is there what the y value is? What's the function doing? What's the y value? So that's what this is all about because we know the x value. In this case, our x is going to -3, so we know where we're looking. We want to know what this function's doing. If we look at it graphically, and here's our x equals -3, when we look at this graphically, we do not get a y value. It's undefined because of the 0 in the denominator. But in this case, the graph does something kind of, funky here because it's not going smoothly along and it's just got a little hole in it that we can patch up. This one's got some problems here is because on one side of -3, this thing's zooming off to infinity, and then on the other side, as we get close to -3, this thing's going down to -infinity. So this is an example where this one's just kind of not working right for us. It's not very good for us. Okay, so that's what we're creating here is a vertical asymptote, that vertical line at -3 in this case. And we're undefined there, and the graph is zooming off to infinities. Okay, so now what's happening here, or how can we see this numerically? What I'm doing here is I plugged the function into the calculator. I'm using my table feature. And then I just started plugging in x values. As you can see, these are x values that are getting closer and closer to -3. At -3, the calculator gives me the error message, which is good because it's supposed to be an error there because of the 0 in the denominator. The catch thing is that as we get closer to 3, what is happening to our y values? In this case, hopefully you can kind of recognize the pattern. Our y values are just getting larger and larger and larger. And that's that zooming off to infinity, positive infinity. This graph is going larger and larger, going up and up and up, getting larger y values. And if I didn't have the graph and I just did the table of data, that's telling me also. So I can look at this graphically, I can look at it numerically with the table of data, and I can see things are not working for us. The values are just getting larger and larger and larger. Then basically what we describe this as the limit does not exist. So DNE, this little DNE kind of thing going on here just means does not exist. So that what we're saying is that the limit, there's no nice number that I can fill in, I can patch in for the hole there. And so what's happened algebraically? We're going to use the same idea, two steps if we can, simplify the expression and then evaluate. In this particular example, when I'm working it algebraically, I'm going to simplify it, so I'm going to factor the top. But when we factor the top, unlike the previous examples, uh, there's nothing that reduces out. This is an x plus 2 on, and this is an x minus 3, and x plus 3. There's nothing that's similar that I could reduce out. So I'm stuck with that 0 in the denominator. So when we have -3, I am stuck with it because I can't reduce this out. And when we can't reduce out, that's a problem for us. And that's when we have limits that don't exist. It's all because our algebra, we're not able to simplify this, reduce this, and to kind of eliminate the problem that we have. And so in this case, that's how our vertical asymptotes happen, is when the things don't factor out for us. Okay, so let's do a quick recap. In the first video, part 1, I did these two examples right here. They created holes. Which basically means if we picked the right point, we can patch it. We can find out what the y value was. We had distinct numbers that we could have. And why was that? Was because we could simplify these. We could factor these expressions, and then we can reduce out the denominator. where the problem was. In this second case, where we got a vertical asymptote, I'm calling that VA. How did we get a vertical asymptote? It was because algebraically we could not factor and reduce things out. So when we can reduce things out, that's great, that's good. We get a whole, we get a limit, we actually get a number. When we cannot reduce it out algebraically, our limit does not exist. We don't get a number. So that's the kind of a quick little recap there. I do have another idea that we have to cover, left and right limits, and that will be in the next video. Thanks, and have a good Hi, Dr. Pat here. We're looking at part 4 of limits, and we're just going to do a little practice here. I got some made a graph, kind of just a little gibberish graph in a way. So this is my function here, and we're just going to look at the limits on using this graph. Okay, so the first example that we have right here is the limit idea as x goes to 0 from the positive side, from the right. So what I'm doing here is I'm going to follow the graph. I'm following the graph as we get closer and closer to x value of 0. The question, remember, the question for limits is what's the y value? So as we get closer and closer to 0, what y value would we pick? I'm thinking a y value of 0. Now here's the theory. This is a cool little theory in this way, is even though there's an open circle here and we don't really use this x value or 0 here, it's open here and it's closed up there. For limits, we don't actually have to have that particular number there. We just need to know what the y values are when we get close. So it's all about getting close rather than exactly at 0. So for us, from the right hand side, the y value that we're getting close to would be 1. Okay, so the limit's equal to 1. On the second example here, we're doing the limit again for as x goes to 0, but this time that little negative sign there tells me that we're going from the left hand side. So as I cruise along this graph and I cruise it, I get closer to an x value of 0. The question is, what is the y value? And the y value that we get close to on this graph was 3. So the limit's equal to 3. And then my next question is, what's the limit as x goes to 0? Okay, there's no plus or minuses on this one. Here's where we're going to have to say does not exist, DNE, and the reason being is one side we're getting closer and closer to 1, the other side we're getting closer and closer to 3. There's a major disagreement. We're having problems here, and so what we say is that the limit doesn't exist. For it to work at a number, our left and right have to be the same number. So this is a break in the graph, and that's creating problems for the limit. We can do the right side and the left side individually, but them together means that it's not working for us, and so that's why the limit as x goes to 0 does not exist. 3 more limits here we got. We got as x goes to -2. What's the limit there? So I'm cruising along this graph. I'm getting close to an x value of -2. I can go from either side. And what happens here is there's no problem on this graph. There's no breaks. There's no dividing by 0. There's no asymptotes. So what happens there is it's just the y value. It's kind of like a case where, yeah, we could do the limit. There's no problem. You could do the limit, but you didn't need to do the limit. So when there's no difficulties, all you have to do is just plug the number in or just read the y value from the graph. And so in this case, that y value is 2, and that's our limit at x equals -2. Now for x goes to -3, so we're playing over here, 1, 2, 3. We're at -3, and look what's happening here. On the right hand side, we're going to -infinity. On the left hand side, we're going to +infinity. Oh, those don't even match, so that's an automatic does not exist. I mean, there is no limit to this one. And then for as x goes to 3, I've got a limit of infinity, and here's why. Because as we go left or right hand side, both sides are going positive to positive infinity. And so even though technically the limit doesn't exist because there's no number, I mean, remember, infinity's not a number. You could write the positive infinity because there's no confusion. It just basically means that both sides of the graph's going way, way up. Whereas on the previous example, they were going to opposite directions, and that's really bad. Okay, so at least if you're going in the same direction, we can at least put the infinity you have. But there's a technicality. Infinity's not a number, so technically it does not exist. Okay, and then we've got two more examples. This time we're doing the long run. So what's the limit as x goes to negative infinity? What's the y value as we go far left on this graph? So that means don't care about what's happening in the middle. All I care about what's happening way out here to the left. This graph looks like to be leveling off to a y value of 1. And so that's what I'd call the limit. What's my y value doing? It's leveling off at 1. And then on the other side here, when we go x goes to positive infinity, that just means to the far right. And I'm kind of looking at this graph and thinking, well, it's probably leveling off here at negative 1. And so that's what I'm doing here. When I'm playing the long runs, to infinity just means to the far right. When we're doing to x to negative infinity, we're going to the far left side. And the key point here is when we do limits, the result is always the y value. We know where to look. We've been told where to look, what the x value is. The question is, hey, what's that y value that we're getting close to? And so that's the idea of limits. I hope this helped, and we'll talk to you later.